HVAC system in a hospital operating room, OR, is far more than a climate control mechanism. It's a frontline system for infection prevention, staff safety, and patient health. Designed in accordance with strict healthcare engineering standards such as ASHRAE 170/2021 and the Facility Guidelines Institute, FGI, OR HVAC systems are among the most regulated environments in building design. In this video, we'll break down everything you need to know into 4 key takeaways, focusing on how these systems are built to maintain sterile conditions, manage airflow, control contamination, and operate efficiently, all while staying code compliant. Takeaway 1. Air changes per hour. The primary purpose of an operating room HVAC system is to reduce the risk of surgical site infections, SSIs, by controlling airborne contaminants and maintaining a clean, stable environment. According to ASHRAE Standard 170/2021, an operating room must meet the following minimum conditions. Air changes per hour shall be a minimum 20 during occupied, surgical conditions, with a minimum of 4 air changes per hour for outdoor, fresh air. The minimum of 4 air changes per hour from outdoor air is to dilute airborne contaminants like bacteria, viruses, and aerosols generated during surgery. This high ventilation rate, mandated by ASHRAE Standard 170/2021, ensures rapid removal of particles and maintains a clean environment, with HEPA filtration capturing 99.97% of particles greater than or equal to 0.3 microns. Infections that result from airborne contamination can be deadly. Studies show that up to 5% of patients develop SSIs, contributing to thousands of preventable deaths annually. That's why the HVAC system must maintain clean air, remove airborne particles, and create an environment that discourages microbial growth. Takeaway 2. Airflow patterns and HVAC layout protect the sterile field. The configuration and movement of air in an OR is not random. It's engineered to flush contaminants away from the patient and surgical team. This is where airflow patterns and room layout come into play. Per ASHRAE 170/2021 and FGI guidelines, supply air must be delivered using a unidirectional laminar flow system, located directly above the surgical table. Here's how it works. Supply air enters the room through laminar unidirectional sealing diffusers, located directly above the surgical table in the sterile zone. Air is filtered through HEPA filters. This clean, filtered air flows straight downward in a smooth column to protect the sterile field. Return air grills are positioned low on the walls away from the surgical zone, typically at opposite ends of the room, so that air exits after passing over the surgical zone. This design creates a vertical airflow path from ceiling to floor, minimizing turbulence and the spread of contaminants. The area directly above and around the patient is known as the sterile zone, while the outer edges of the room are considered non-sterile zones. HVAC airflow is engineered to always preserve that boundary. Takeaway 3. Pressure relationships are engineered to prevent contamination. An equally important part of OR HVAC design is managing room pressure relationships. In a surgical suite, air should always flow from the cleanest areas to the less clean areas. That means the operating room itself must be kept at a positive pressure relative to adjacent spaces. According to ASHRAE 170/2021, the operating room must be maintained at a minimum positive pressure differential of plus 0.001 inches water gauge relative to adjacent areas, including corridors, anterooms, scrub areas, and nursing stations. Here's how the pressure cascade typically works. The operating room is positively pressurized compared to corridors and adjacent support spaces. Sterile storage rooms are also positively pressurized to protect clean supplies. In contrast, soiled utility rooms or decontamination areas are kept at a negative pressure to contain contaminants. These pressure differentials are actively monitored using sensors and pressure gauges. If pressure drops below the required threshold, alarms are triggered to alert staff. This directional airflow ensures that airborne particles from dirtier areas cannot flow into sterile spaces, critical for infection control. Takeaway 4. Temperature and humidity control. Operating rooms must maintain temperatures between 68 to 75 degrees Fahrenheit, 20 to 24 degrees Celsius, and relative humidity between 20 to 60% to ensure patient safety staff comfort, and infection control. Tight control prevents microbial growth, high humidity, or static electricity, low humidity, with building management systems, BMS, ensuring precise regulation per ASHRAE and FGI standards. System temperatures can be set lower depending on the specific requirements of the operating room or staff. Recap and final thoughts. To summarize, a hospital operating room HVAC system isn't just about heating and cooling. It's a critical infection control tool. Let's quickly review the 4 key takeaways. 1. Infection control. HVAC systems prevent surgical site infections using HEPA filtration and airflow control by requiring a minimum air change rate, which is defined by ASHRAE 170/2021. 2. Airflow and layout. A vertical laminar flow pattern with low wall returns protects the sterile field by continuously removing contaminants. 3. Pressure management. Maintaining a minimum positive pressure. Differential of plus 2.01-inch water gauge is vital to keep clean air in and contaminated air out. 4. Temperature and humidity control. Maintaining precise temperature between 68 to 75 degrees Fahrenheit, 20 to 24 degrees Celsius, and humidity, 20 to 60% RH in hospital operating rooms, is critical for patient safety, staff comfort, and infection control. These conditions, mandated by ASHRAE 170/2021 and FGI guidelines, prevent microbial growth, reduce static electricity risks, and ensure optimal surgical outcomes. Building management systems, BMS, with thermostats and hygrometers enable tight control, using reheat coils, humidifiers, and dehumidifiers to maintain stability, even in variable air volume systems during setback modes. This factor underscores the balance between environmental precision and energy efficiency in OR HVAC design. By understanding these core principles, you'll have a strong foundation in the design, function, and control of one of the most important systems in a healthcare facility.